talk about infrared spectroscopy, IR spectroscopy. Those of you who are on campus who have done labs in the lab have seen and used an IR so far. We're going to talk a little bit about how we can use IR to determine what functional groups are present in a molecule. So in IR, we're looking at bends and stretches in a molecule. Those bending and stretching modes absorb in the infrared range of the electromagnetic spectrum. And it's only going to interact with dipoles, right? So the bigger the dipole, the more that light is going to interact with it. So the bigger the dipole is, the larger the absorbance of that light is going to be. Again, the big killer app for this is that I can tell functional groups pretty much at a glance. It's a really quick assay to run. It only requires a little tiny bit of sample. I can't really tell how many bonds I have a lot of times. So I might be able to tell if I have a CH bond, but not how many CH bonds that I have. But it's also non-destructive. So like most spectroscopy, I'm not going to lose material simply because light is passing through it. Much like polarimetry, the units that we're going to use for IR are a little bit strange. So we are going to use wave numbers. Wave numbers are inverse wavelength. So to back up, light is characterized by wavelength and frequency, and those are inversely proportional, right? C is a constant, the speed of light is constant. And so our inverse wavelength looks like this. It's actually centimeters. It's the reciprocal centimeters. The range that we're usually talking about in IR is about 4,000 to 400 inverse centimeters. So, like I said, IR is essentially mostly about stretching bonds. And sometimes we can think about bonds as two balls connected by a spring, right? The bonds of the spring. And so let's talk about springs a little bit. So imagine I have a wall here, and I've got a ball connected to the wall by a spring. And I pull on it with some force, and then I watch it go like that. If you listen closely, you can hear it. Now, here I've got a thicker string. So this is like a car strut or something, right? Steel, I'm talking, like that big around. If I pull on that spring with the same force, then how is that going to vibrate differently? Well, what we're going to see is that it's going to be displaced a lot less, and the vibration is going to be a lot faster, right? It's going to be like ding instead of wang, 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 right? This top one, wang, wang, wang. This middle one, bing. So higher frequency, right? That's what frequency is, how many times it goes through, back and forth. But let's say I go back to my thin spring, and now I put a giant mass on the end of it like this. Now if I pull that, that's going to be like wong, 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 right? Because it's kind of harder for that big mass here to change direction, I guess is the way I think of it. And so a thicker spring should give me a higher frequency, but a greater mass should give me a lower frequency. So this essentially takes us back to Hooke's law for springs. You might remember from your physics class. So for a spring, our big two criteria are K and this mu. K is the force constant, and that's essentially how thick our spring is. So the greater K is, the greater our frequency is, right? So that tracks. Here, because we're not dealing with one fixed object and one moving one, we're dealing with two moving ones, we're going to use this idea called reduced mass. Reduced mass is the product of the masses divided by the sum of the masses. So if I had like CH, C is 12, H is 1, 12 times 1 over 12 plus 1 would be like 12/13. Okay? But the greater the reduced mass, the lower the frequency we're going to see. As a quick example of how that works, so here I've got some typical frequencies of a CH and some CC bonds. If I compare my CH with my CC, the CH stretch is a lot higher than the CC stretch at 1200. So that is an indication of its relative to reduced mass. So the reduced mass of the CH is again 12 times 1 over 12 plus 1. So this. The reduced mass of a CC bond is 12 times 12 over 12 plus 12. That equals 6. The reduced mass of the CC is greater, and so the frequency of the CC is greater than the CH. But if we compare the single bond, triple bond, double bond here, you can notice that the stronger the bond gets, the higher the frequency gets. And so that's an example of our wave numbers being proportional to, in this case, the square of the force constant. So how strong that bond is. The stronger the bond, the higher the frequency.